Alright, so hello everyone, this is the second lecture and it is going to be on fundamental of digital electronics. So in digital electronics, it's a very vast area, right? You can study quite a lot. There are so many topics under this. But we have restricted ourselves to some of the basic concepts of a digital electronics. So I have divided this lecture into two parts. So part of the topics we are going to study today, and the remaining topics we are going to study in the next class. Okay, so in this class we are going to study number system, specifically your binary numbers, and then we are going to study about Boolean algebra, reducing the Boolean functions using K-map, logic gates, and combinational and sequential circuits. Okay, the remaining topic, something like ADC or DAC, so analog to digital conversion or digital to analog conversion, all that we are going to study in the next class. Okay, so this is going to be the very basic digital electronics class. Now, there are basically two types of signals. One is called as your analog and the other one is called as your digital signals. So analog signals, they are continuous in time. Okay, you can see analog signal here, so it is continuous in time, right? So therefore within a given time frame, okay, within a given time frame it can have infinite number of values, right? You may have a value of let's say voltage at 1 second, then at 1.0001 second also you will have a different value, right? So within this time frame or time period, your analog signal can have infinite number of values. And most of the real world activities, they are analog, right? So if I jump, right, if I'm jumping, so I will have different height from the ground at different point of time, right? So everything that we see around us in real world, they are mostly analog, right? On the other hand, you have digital signal. So these digital signals, they are discrete in nature or discrete in time, and they can only have two values, right? At any point of time, they can have only two values, right? Either it would be 0 volts or it would be 5 volts. You cannot have any value between them or any other value, right? So all the machines or basically the computers, they can understand this digital signals. Now if we talk about machines in very layman terms or in very general, a machine could only understand either it is on or off, right? So if it is getting no signal or no voltage, it is off, or if it is getting a voltage, it would turn on, right? So a digital device or a machine could understand only digital signals. Now most of the avionics system that we are going to study, they are all computer based, right? So they could understand this digital signal only. They cannot understand analog signal. which varies continuously with time. So that is why it is important to kind of understand or develop a basic concept of digital electronics before we study about the different avionics system in detail, right? Now, to start with the first topic is your number system. Okay, so you have several number system. You have decimal, you have binary, you have octal, hexadecimal. So decimal number systems, they are base 10 number system. Okay. Base 10 number system. Okay. So you can represent any number in units, tens, hundreds, thousands, and so on, right? You can even have decimal number, negative power of 10. Okay. So these decimal numbers, they represent the real world or analog signal. Okay, which humans understand or which we understand. Now binary number is base 2 system, right? So binary numbers, they can be understood by the computers, right? And they have, or any number or any value, it can be represented by either 0 or 1, right? So binary numbers, they are base 2 number systems, and either you could have 1 or 0. That is, you could represent any value by 1 or 0. So for example, if we have a similar or the same decimal number, 5, 6, 7, 8 in decimal is represented as this entire binary. Right? So you could see you have only ones and zeros. Right? Octal number system, they are base 8. So octal 8, it is rhyming, right? Quite similar. They have similar pronunciation. So octal number system, they are base 8 number system. So these numbers or numbers in octal number system, you could have 8 values, that is starting from 0 to 7. So you could represent any number by 0, 1, 2, and so on up to 7. So altogether you have 8 numbers by which you can present or represent a octal number. So the same number 5, 6, 7, 8 in decimal, it is represented by 13056 in octal. Okay, between 0 to 7 you can use numbers. We'll study about how to convert these number from one number system to another number system, but mainly you should note, or you should have an understanding about which one is base 2, which one is base 8, and so on. Similarly, you have hexadecimal number system. So hexadecimal number system, they are base 16 number system, right? So any number in hexadecimal, it can be represented by numbers from 0 to 9, that is 0, 1, 2, so on up to 9. or by alphabets from A to F, right? That means A, B, C, D, so on up to F. Okay. So the same number 5, 6, 7, 8 in decimal, it can be represented as 162E in hexadecimal. Okay. So decimal number system, they are base 10. Binary number system, they are base 2. Octal number, they are base 8. Hexadecimal, they are base 16. Okay. Now, let's take one of them at a time and see how we can convert them. Okay. So let's say if we have a decimal number and we want to convert it into binary. Okay. So for example, I have taken 29 as my decimal number. Okay. To convert it into binary, you divide by 2. Successive division by 2. Okay. Let me just turn on the arrow option. Should be visible, right? Because I'm using a pen here, so even the location of the pen, it will be visible, hopefully in the slides. Otherwise, I'll be marking. Right. So to convert a decimal number into binary, we have to divide by 2, successive division. So here on the right hand side, you could see I've taken the number 29 and I'm continuously or successively dividing it by 2. Right? So if I divide it by 2, I'll get 14. Right? So it is 14 multiplied by 2 is 28. So I'll be left with a remainder 2. Remainder 1. Right? Again, if I divide, I can divide it by 2. So I'll have 7 and the remainder will be 0. So like that, you continue to divide it by 2 until you get 1 or 0 at the end. Okay, and then you start considering the number from bottom to top, right? So 29, it can be represented as 0, the last number, then 1, the second last, then again 1, which is the third last, and then you have 1, which is the third last, 0, 1, like that. Okay, so if the first digit or the most significant digit, we call it, or this one, it is 0, you can ignore it. Okay, so 29, it can be converted into binary, and its binary equivalent will be 1, 1, 1, 0, 1. Okay, so you just have to divide it by 2 and consider the remainder from the bottom to top. Now, if I convert the binary number back into decimal, what I have to do? I have the binary number 1, 1, 1, 0, 1. Okay, so I will take 2 because these are binary numbers, they are base 2 number system. So 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, and 2 to the power 4, like that, and multiply them with the corresponding numbers. Okay, something like this, right? 2 to the power 0 multiplied by 1, and then the next number is 0, so I've multiplied it by, essentially it's going to be 0, but just for understanding I've multiplied it. And then the next number is 1, so I've multiplied it by 2 to the power 2. And then similarly all the binary digits or binary number, I multiply it. If you have more, if you have a bigger number, binary number, you can continue, right? You will have 2 to the power 5, 2 to the power 6, and so on. So if we do the calculation, you should get 29. So just in exams, if I give you a binary, if I give you a a decimal number and ask you to convert it into binary. So you have done the conversion, but you are confused whether your answer is correct or not. So you can convert it back into decimal and just check or verify your answer, that whether you are getting the same decimal number or not. Okay. But this is quite simple. It shouldn't create any confusion, but just in case. The next number system or the conversion is from binary to octal. So binary is base 2 and octal is base 8. Okay, so we have to convert from base 2 to base 8. So let's say this is the binary number we are given. Okay, and if we have to convert it into base 8. So base 8, that means 2 to the power 3 is 8, isn't it? So we will start from the right hand side and pair 3 binary numbers together. Okay, like that. So I've divided it into pair. So 1 0 0, then the next pair is 1 0 1 and 1 1 1, like that. Base 8, so 2 to the power 3 is 8, so I am pairing 3 pairs. Now for example, if you have maybe a number, I will consider a singular number, like that. So while pairing, what you see, maybe you don't have, you have only 2 numbers, so you can add a 0, okay, at the end or for the last pair. Okay, so that way we have done the pairing of 3 numbers, and then we have to convert them into decimal. Each of the pair you convert into decimal. Okay, so if I convert 1 0 0, so it will be 2 to the power 0, 2 to the power 1, 2 to the power 2. So 2 to the power 0 multiplied by 0 is 0. I mean they will be 0. So I'll be getting 4. Similarly 2 to the power 0, 2 to the power 1, 2 to the power 2. Okay. So this will come out to be 2 to the power 0 is 1 multiplied by 1. It is 1. The second will be 0 plus 2 to the power 4 multiplied by 1, it will be 4. So 4 plus 1 is 5. And the same way you can convert it the third pair. Okay. So 2 to the power 0 is 1 multiplied by 1 is 1, and 2 to the power 1 is 2 multiplied by 1 is 2, and 2 to the power 2 is 4 multiplied by 1 you get 4. So 4, 5, 6 plus 1, 7. Okay. So this is my decimal number. Sorry, octal number, base 8. 754 is my octal. So this binary number, I can convert it into octal this way. Now if you want to do the reverse, you have a binary number and you have to convert it in, you have an octal number and you have to convert it into binary. So you can take individual, you can split out the numbers. So for example, I'm taking the same number 754. So I have spread it out 754, right, and represent each of these numbers, octal numbers, by 3 binary number. Okay, so 4, it is 1 0 0, 5 is your 1 0 1, okay, and 7 is 1 1 1. So this will convert your octal number into binary. Okay. So you take each octal number and represent it by 3 binary digits or 3 binary numbers. Now the next conversion. So the next conversion is from binary to hexadecimal. So binary is base 2 and hexadecimal is base 16. So 16 will be 2 multiplied by 2 is 4, 4 multiplied by 2 is 8, 8 multiplied by 2 is 16. So basically it will be 2 to the power 4. So now I will select 4 pairs from RHS, right hand side. Okay, so you start from the right hand side and you select 4 pairs. So the 4 pairs will be 1 2 3 4. This will be the 4th pair, 1 2 3 4, like that. Okay. So I've mentioned it here, the 4 pairs, and then convert it into hexadecimal, right? So for conversion, so you can convert it into decimals first. So 1011 is 11. Okay, again you can verify 2 to the power 0, 2 to the power 1, 2, 3. Multiply them, you should get 11, right? And 1001 is 9, and 1000 or 000 is your 8 in decimal. Okay, and 1101 is 13, right? So you have converted it into decimal. Now in hexadecimal, so you can see here I have put the table for converting decimal to hexadecimal. So 0 in decimal is 0, Okay, 1 is 1 all the way up to 9. Hexadecimal you can represent from 0, you can use 0 to 9 and then A to F. Okay, so up to 9 the conversion is the same, right? In decimal also it is 9, in hexadecimal also it is 9. The changes start from 10. So 10 in decimal is represented as A for apple, right? In hexadecimal. 11 is represented as B for ball, right? So A, B, C, D, E, F all the way up to 15, right? So you can maybe jot down the table, or you can create a table and then convert this decimal values which you have found. So up to 9 it is the same. I'm getting 11. So 10 is A, 11 is B, right? So 11 is B. Next one is 9. So 9, up to 9 I don't need to worry. In decimal also it is 9, in hexadecimal also it is 9. So again the next number is 8, so don't need to worry. Right. The next number is 13. So 9 is okay. 10 is A, 11 is B, 12 is C, and 13 is D. So it should be D in hexadecimal. Okay. So I have mentioned it here. So this is your base 16 or hexadecimal number D89B. Okay. Now to convert it in reverse order, that is, if you are given with a hexadecimal number and you have to convert it into binary. So the first step I will do is take one hexadecimal number and convert it into decimal. Okay, so I will take 3. In decimal it is 3. F, so this is your hexa and this is your decimal. So F is 15. So F is 15 in decimal, and D. So D is 13 in decimal. Okay, and then the next step would be to write these decimal number into binary of 4 digits or 4 numbers, because hexadecimal is 16, base 16, right? So we have to represent them by 4 binary digits, right? So 3 can be represented as 0, 0, 1, 1. 15, it is 1, 1, 1, 1. All 4 digits, they are 1. 13 is 1, 1, 0, 1. Right? So altogether, it will be, this will be your binary number. If you practice maybe 3 or 4 of these conversion problems, the concept will be clear. Okay, it's not difficult, just you have to maybe practice a few questions. Okay, Just 3 or 4 questions and you will be sorted. Okay, so there are obviously other conversions. So if you want to convert from octal number to decimal number system, so you could convert the octal number into binary first, and then from binary you can convert it into hexadecimal. Okay. And if you want to do the reverse, that is hexadecimal to octal, you can convert the hexadecimal into binary, and then from binary you can convert it into octal number, right? So it will involve a number of steps, but you can use this way to convert any number system from one number system to another. Okay. Now, so I would suggest you all to practice at least 3, 4, like try all the conversion from one to another or another and backwards, right? So try like 4 or 5 questions. It won't take long, but it will clear the concept, what you actually are doing. So let's move on to the next topic, which is logic gates. I think you all might have studied about logic gates, or you must be aware about logic gate. But just to give you a little introduction, I will take this topic. So logic gates, they are physical electronic devices. That means they are actual electronics. They exist, right? They are small chips, right? Some rectangular chips like that you might have seen or even used at some point, right? So they are actual physical electronic devices which exist, and they are used to perform logical operations on one or more binary inputs, right? So you could perform logical operations on one or more binary input, and the logic gates will produce only single binary output. So binary output means it could be either 0 or 1, right? So it can perform binary operations on one or more binary inputs, and it will produce a single output. The single output would mean in binary it could be either 1 or 0, right? Only 2 of the outputs you would get, right? So in the slide you could find some of the basic logic gates. So the first logic gate is called as your AND gate, A-N-D, AND gate, right? So the basic logic or the concept is, if A and B are 1, output is 1. Okay, so AND gate would mean both A and B are 1, then my output will be 1, right? So this is the truth table. Okay, because it signifies the truth, that is why we call it truth table. Okay, so as you can see, the in the first one both inputs are 0, so my output is 0. When B is 1, then also output is 0. When A is 1, then also the output is 0. Output is 1 only when both A and B, they are 1. Okay. The second logic gate is OR gate. So the same concept will apply. If A or B is 1, the output will be 1. So if A or B, I will add a line here, or both. If A or B or both, they are 1, then my output will be 1. Okay, so let's check the truth table. So A is 0, B is 0, output is 0. A is 0, B is 1. So A or B, either A or B is 1. My output is 1. Similarly, the next case, A is 1 and B is 0. So again, my output is 1. And the last case, where both A and B are 1, then also my output is 1. So if A input or B input or both, they are 1, my output will be 1. Okay. The third logic gate is called as XOR, or exclusive OR. Okay. So exclusive OR is similar to your OR gate. Just this extra statement, or whatever we have added, is not there. So in exclusive OR, only if A or B is 1, the output is 1. Right? So B is 1, output is 1. Okay, A is 1, the output is 1. But the last case, where both A and B, they are 1, the output is 0. Okay, so exclusive OR, it means only when A or B is 1, right, then my output will be 1. If both A and B are 1, then my output will be 0. It will not be 1. Okay, so that is the exclusive OR gate. And OR, exclusive OR, quite simple. Right. The next set of basic logic gates, we have NOT gate, or sometimes you also call it as inverter or complement. Okay, so the basic working of this logic gate is, if you have A, you will get inverse of whatever you are applying. If you are applying 1, you will get 0 as output. If you are applying 0, you will get 1 as output. It will just reverse your output, right? Invert your output. So basically, the output is represented as A bar, or you could also sometimes see it as A dash, like that. Okay. So if the input is 0, the output will be 1. If the input is 1, the output will be 0. Just the opposite. So using the AND gate and OR gate along with this NOT gate, we can have a few more gates. NAND gate, or you could also call it as NOT AND right? So the output will be just the inverse of AND gate, right? So in the previous slide, AND gate, it was when A and B, they are 1. So whatever output you are getting here, right, they will be just inverted. So if we see, they are inverted. In the case of AND gate, both A and B, if they are 1, output is 1, right? This was the only case when my output was coming out to be 1. The rest of them, they were 0. So if we use not AND gate or NAND gate, in short, it will just reverse the output. All of them, they will be 1 and the last one will be 0. Right? Similarly, NOR gate or not OR, right? Same thing, whatever output you were getting for OR gate, it will reverse, or OR gate will be, in the case of NOR gate, you will get inverse of OR, or if you understand, opposite of OR gate output, right? So whatever you were getting for OR gate, the opposite will be for NOR gate, NOR, right? So this is the truth table. Now, the next topic is digital logic families. So the logic gates, they are obviously physical electronic devices, as I mentioned, right? They are fabricated, or they actually exist. So you would have some components which you connect to make this digital logic. So the basic component that is used to fabricate the digital logic ICs or integrated circuits, they are called as transistors, right? So again, there is a entire theory about transistor, how they operate, different types of transistors, right? But we are not going to go into detail. Now in the class notes, if you are interested, I have provided a link, a web link. So you can go on to that link, and it has, not in detail again, but it has explained how the transistors operate and how they are used in digital ICs. Right? You can go through that if you like, but it is not mandatory. Now, transistor, they basically act like a switch, okay, and they can be operated in different modes. So for implementing NOT gate, right, for implementing NOT gate, we use transistors. In inverting mode. Inverting mode. Okay. So whenever the input to the transistor is high or 1, the output will be low or 0, and the reverse. If the input is low, the output will be high. Okay, so transistors are basically used to fabricate these digital logics, right? So other gates also, like AND gate, OR gate, so using combinations of transistors. So NOT gate, for fabricating NOT gate, you can simply use one transistor, right? But for AND gate and OR gate, you would need a combination of transistors. Okay. So based on the different technologies or different uh, components that we use. So again, transistors were used in older days also, but now we are trying to reduce the size of transistors. Yeah. So now the entire processor or your CPU, it can be fabricated on a very small chip, right? You all must be aware about that, right? So now the mobile phones, initially the computers, they were so big, right? But now we have a computer in every hand, right? Mobile phones. So this is because the transistors have been, or different technologies have been used to reduce the size of the transistor, right? So based on the different technologies that we use to fabricate these logic ICs, you can divide them into different digital logic families. So you have transistor logic, which is the oldest technology, and they use bipolar junction transistor. Right? Maybe now also you could find they are not used in fabrication, maybe making a computer, they are not used, but maybe in the labs you could find ICs fabricated out of this TTL technology. Then you have emitter coupled logics. They have the advantage of high speed. Okay. Metal oxide semiconductor transistor. So they are all transistors, right? But they have a different technology to reduce the size of transistors. Okay. So metal oxide transistors, they have this advantage that if you need high component density, that means within a small area, if I want to fit lots of component or lots of transistor, I can use metal oxide semiconductor transistors to fabricate that integrated circuit. Similarly, you have complementary MOS or metal oxide semiconductor or CMOS. Right? So CMOS are used in most of the digital devices, your digital cameras, your personal media player or MP3 players. Right? So these are mostly used nowadays, CMOS. Okay. Now, having a basic idea about the logic gates, let's move on to the combinational logic. Right? So logic circuits. So we have studied about gates, but using those different gates, logic gates, we need to build a circuit. Right? So logic circuits, they could be of two types. You could have combinational logic or sequential logic. Now, in the case of combinational logic, it consists of logic gates whose output at any time are determined from only the present combination of input. Okay. So combinational circuit, their output depends on present input. Okay. Whatever is the present input, according to that, the combinational logic circuit will produce the output. Okay, so a combinational circuit performs an operation that can be specified logically by a set of Boolean function. Okay, so whatever is the logic that is being implemented, it can be represented in form of a equation, or we call it as Boolean function. Okay, so the logic of combinational circuit, they can be represented by a equation or a Boolean function, right? Now, the second type of digital logic circuits, they are called as your sequential logic circuits, right? So sequential circuits, they have a storage element or a memory, right? Or they have a memory along with the combinational circuit. So along with the combinational circuit, you add a memory device or a storage element, right, which will store the output. So for sequential logic circuits or for sequential circuit, the output, it depends on present input, right, whatever you are applying, and the status of the memory, whatever data is stored in the memory, that will also affect the output. Or we can say the previous input. Okay, so the output of sequential circuit will depend on present input and the previous input, right? Because according to the previous input, there is some data in the memory which will affect the output. Okay, so let's start with the combinational circuit. We'll study about the memory maybe a little later. Okay, right. So combinational circuits, they are basically combination of logic gates, right? So combination of logic gates, right? So if you want to produce a certain output based on the input, you would use different logic gates, connect them together to produce your output, right? So combinational circuit are basically combination of logic gates, right? So as we mentioned that obviously combinational circuit, they will have output depending on the present input, and along with that, the second property is they can be represented by Boolean function. Okay, they can be represented by an equation or a Boolean function, right? So how do we get that Boolean function? So basically your Boolean algebra, it is used, so there are some formulas, right, so which can be used to simplify a Boolean expression, or which can be used to build your Boolean function, or to write the equation representing your circuit, right? So AND gate, they are represented by dot. right? So if you have two input, A and B, and if you have connected it using AND gate, so you would have a dot. OR gate, they are represented by a plus sign, A plus B. So for example, you could see I have like three input, right? I've connected them using, this is your OR gate and this is your AND gate, right? So B and C are coming from or are input of OR gate. So OR is represented by plus sign, so it will be, the output will be B plus C. Okay, and then this is going to the AND gate, and from this side you are getting A, right? So AND gate is represented by dot, so here it will be something like this. We can write the Boolean function of this circuit, right? So it will be A dot and B plus C. Okay. Now, very often while building your circuit or while fabricating your circuit, you would keep on adding different gate. Okay, so after this step, my output should invert. So I should add a NOT gate. Then I need to add two input. So you keep on adding a large number of gates to implement a logic, right? But we also have to fit that entire circuit onto a very small chip. So we should reduce the number of gate or use the least number of gate to implement the same logic or the same output. So there is something called as binary arithmetic, right? Or binary algebra. So there are some formula based on which we can reduce the circuit, right? So in this example, in the two figures, you could see this is the output of the first figure, and if I call it as figure number 2, so this is the output of the second figure. So if you compare, the outputs are the same, but if you count the number of logic gates, so in figure number 2 we are using 1, 2 and 3 number of logic gates, whereas the same logic, right, the same output, it can be produced by using only 2 logic gates. So that is why we always need to use binary arithmetic or those formulas to reduce the circuit. Okay. So these are the formulas, right? Quite simple. I'll go through them, but yeah, some of them you will remember, some of them I will ask you to remember, right? So the first theorem, right, theorem or law, whatever you want to call it. So the first theorem is called as your commutative law, right? So if you have A plus B, right, so you could also write it as B plus A, okay? And if you have A dot B, it can also be written as B dot A, right? That's simply your basic commutative law. You could reverse the two inputs, right? A dot B or plus B, it can be written as B plus A or B dot A, the other way around. The second theorem is your associative law. So the associative law is A plus B plus C. It can be represented or it can be written as A plus B plus C. And the same thing is for dot. If you have A dot B dot C, you could also write it as A dot B dot C. Right? So you can just rearrange your Boolean function. The third theorem is your distributive law. So if you have A dot B plus C, now here we have combination of AND and OR gate, right? So you could maybe consider it similar to multiplication, right? So if you have A multiplied by B plus C, you could write it as A multiplied by B plus A multiplied by C, like that. But the same thing for plus also. If you have A plus B dot C, again you could consider it as multiplication. So A plus B dot A plus C, like that. Okay, so you can spread out or you can open the brackets like that. The fourth one is easy one. A plus A is A and A dot A is A, right? If you have the same input which is getting AND or the output will be the same as your input. Okay. Theorem 5 is unnamed, so it is A dot B plus A dot B is A, right? If you are repeating, it is A. And the same thing for A plus B dot A plus B is A. Okay, so just to specify, by dot I mean it is AND gate, okay, and the plus signs, they mean it is OR gate. Right, then you have redundancy law. You can go through it. You have theorem 7. Yeah, so one of the theorem which is important is your De Morgan's law, right? And obviously you should have an idea about all the laws. You may get questions to solve or reduce a Boolean function or equation using these laws which you have, right? So the slides are there, you can go through them, or you can refer back if you need these laws, right? Now just to show you how you can solve using the Boolean algebra some of the questions. So this first problem is to simplify the following Boolean function to a minimum number of iterations, right? So here you have x and there is nothing, so it would mean x dot, right? X dash or x bar plus y. If you do not have anything in the middle, it would mean you have a dot, right? So dot means AND gate and plus means OR gate, right? So using distributive law that we have just seen, we can spread this or open the brackets, right? As I mentioned, that you can consider the dot or plus before the bracket as multiplication, right? And open the bracket. So if I open this bracket, I will get x dot x dash plus y x dot y or xy. We can also write it as x dot x dash plus x dot y. So if there is nothing, it means dot. Okay. So then according to theorem number 9, if you have the complement of the same variable multiplied by the variable, it is 0. So you have x multiplied by x complement, or basically x dash means not of x, not gate of x. Okay, so it is 0. So basically we can make this 0. So finally we can reduce the function or the given Boolean expression to simply x, y, or you can also call it x dot y. Okay, so just by using a single gate, so here you are using 1, 2, 3 gates, but here you can represent, or you can get the same output using a single gate. Similarly, let's see how we can reduce this second problem. So you are given with, the function is given as x plus x dash y. Okay, so what we can do is, using theorem number 8, we can refer back to it. We can rewrite the first term as x dot 1. So x dot 1 is simply x. Okay, so I'm just writing the first term, expanding the first term. Then using theorem number 8 only, the second or the first part of theorem number 8, if I have x plus 1 also, x plus 1 is also x, right? So here I'm writing it as y plus 1. I can write it as equal to 1. Okay, so I will replace this 1 by 1 plus y according to the second theorem, right? So I've replaced it by 1 plus y. Then using another theorem, theorem number 3 to be specific, we can expand the bracket, right? So if I expand, x dot 1 is x, so I've just written it as x plus x dot y will be my second term, and then you will have x dash y. Then we can take y common. So from the last two variables or the parts, we can take y common. So in the bracket I'll be left with x plus x dash, and this x plus x dash is 1 according to theorem number 9. So finally I will get the reduced form will be x plus y. Yeah. So again we were using 3 gates here, so now we can implement the same logic using a single gate. Now, remembering all those formulas, those theorems, it is challenging, right? So there is another way of reducing or simplifying your Boolean expression, right? Which is simpler, or which is comparatively easier. So that is called as your K-map or Carnot map. So in short, we call it as K-map. So K-map is basically a pictorial representation of logical expression. So pictorial means you could see how the expression is implemented, right? Using some pictures, some graph, you represent your data or your function. Okay, and using that we can reduce the Boolean expression. So for example, we are given with two variable K-map. Okay, so this function, the Boolean function, it has two variables, right? If you see, you have A and B only, right? So you have two variables. So if you have like two variables, what we have to do for K-map, or how we can use K-map to reduce the function, what we can do is, the first step would be to make this kind of a table. Okay, so since you have two variables, so you should have 2 to the power 2. That means 4 boxes, let me call, right? So you should have 1, 2, 3, 4 boxes. Okay. Then the next step is to label these boxes. So what we do is, we have two variables A and B. So on one side we will take A, and on the other side we will take B. And the first block will be 0, the second block will be 1. Okay. Similarly, along the horizontal direction, or along the B, we will have the first block will be 0, the second block will be 1. Okay. Now the combination of A and B. So the first block here. So in the first block, the value of A is 0 and the value of B is also 0. So if it is 0, we represent it by A dash, A is 0, so A dash, B is also 0, so B dash. For the second block, the value of A is 0 and the value of B is 1, right? So A is 0, that means A dash, and the value of B is 1, that means B, right? So if you have 0, you would write as A dash or B dash, and if it is 1, you would write it as A or B, depending on what is the value of A, right? Similarly, for the third box here, the value of A is 1, right? So A is 1 and the value of B is 0. So A is 1, that means A, and B is 0, that means B dash. So you will write it as A, B dash. Similarly, for this block, the value of A is A is 1 and the value of B is 1. So A is 1 and B is also 1 for this box. So I can write it as A, B, right? So at the corner you could write it as AB. Right? So after you have done the labeling, what you can do is, you can start filling the table. So my first term, or the first term in this Boolean function, is A dash B, right? So in this table I will have A dash B is here, right? So I will put 1 in that box. The next term is A B dash. Okay, so I will put 1 in the corresponding box. So A B dash is this one, so I have put 1 in this box. Similarly, the third term is AB, so I have put 1 in the corresponding box, right? The next step is to pair ones. Okay, so we have to form pair of ones. So you could have a pair of 2, or you could have pair of 4, then pair of so basically you could have pairs in the power something like 2 to the power 1, 2 to the power 2, 2 to the power 3. So 3 is 8. You can have 8 number of ones, you can pair them, right? And 2 to the power 4 is 16, right? So you cannot have maybe 5 or 6 pairs, right? 5 or 6. You cannot have 5 or 6 number of 1, right? So in this example, I could pair maybe 2 ones. So pair adjoining ones. Adjoining means next to each other. Okay, so here we could have 2 pairs, right? So I'll have to erase this, then only I'll be able to show you. So one of the pair is this, right, adjoining one, and the next pair is this one, right? Now we have to write the reduced form of this. Now the brown circle, right? The brown circle, it can be reduced, and the reduced form will be A. How we can get this A? So the brown circle is covering these 2 blocks. Yeah. So for these 2 boxes, the value of A is 1. The value of A in this direction, it is 1, right? Which is not changing, which is fixed, right? The value of B, so across these 2 boxes, the value of B is changing from 0 to 1. So if the value of any variable in the K map is changing from 0 to 1 or 1 to 0, then we can cancel that variable. Cancel or ignore that variable. Okay. So since the value of B is changing, so we can ignore B, or we can cancel B variable. Now value of A is fixed. What is the value of A? It is 1. So I will get A. So the reduced form of the brown box will be A. Similarly, the reduced form of the blue box. Okay, so the blue box is covering these two boxes along the vertical direction, right? So for reducing this, so the value of b here is 1. Okay, so maybe okay, right? So these two pair are covering this box and this box. So the value of b is 1, which is fixed. Okay, it is not changing. What about the value of a? The value of a is changing from 0 to 1 for the blue box, right? So if it is changing, we can cancel or ignore a, and the reduced form will be b. So the value of b is 1, so it means b. If the value of b is 0, if value of b is 0, then we would get the reduced form will be b dash. Okay, but here for us the value of b is coming to be 1, so we will have b, and the final reduced expression of this Boolean function, it will be c is equal to a plus b. So I got a and b, right? So it will be simply you add them together, a plus b. Okay. Now, lastly, let's consider a 3-variable K-map. Okay, so we have a, b, and c in this Boolean function, right? We have 3 variables, a, b, and c. So how many number of boxes we should have in the K-map? So it should be 2 to the power 3. That means 8 number of boxes. Okay, something like this. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8 number of boxes. Okay, next step is to label the boxes. So since we have 3 variables, isn't it? Previously we had 2. So one side, so in the previous example we took a on one side and b on the other, but now we have 3 variables. So we will take one of the variable along this side. So I've taken a in this direction and the remaining 2 variable in this direction, b and c. Okay, and I will label along the vertical direction. I will label the first box as 0, the second will be 1. Then along the horizontal direction, along this direction, I will label the first box as 0, 0, right? So the first number is for b, the second number is for c, right? Second box, I will label it as 0, 1. The third box, I will label it as 1, 1. And then 1, 0. Right? So just be careful about labeling the boxes along the horizontal direction. First box is 0, 0. Second box is 0, 1. Third box is 1, 1. And then you have the fourth box as 1, 0. Okay, if you label it wrong, your entire solution will be wrong. Okay. Now, third step is to write down the corresponding boxes. What do they mean? So the first box, A is 0. So for the first box, the value of A is 0. The value of B and C is also 0. So 0 means everything will be complement or dash. So A is 0, A dash, B is 0, B dash, C is also 0, so C dash. For the second box, the value of A is 0, the value of B is 0, and C is 1. So A dash, B dash, C. Like that, we label all the boxes. Okay. And then we have to consider each of them, each of the variable in the given Boolean function. So in the given Boolean function, the first variable is, or the first part is A dash, B, C dash. So find that box and put 1 in that box. Similarly, the second variable is A dash, B, C. So I put a 1 there. The third variable is A, B dash, C dash. So again, I've put a 1 in that box. And the last variable is A, B dash, C. So I put 1 in that. Then the next step will be to pair them. Okay, to form the pair. So our intention is to form a pair of 1 with largest number of 1. Right? But in this case, we could see that we could have only pair of 2 ones. Right? One is this one and the second is this one. Okay? Adjoining ones. You cannot pair these two. Right? You cannot pair like that. You have to pair along the vertical or the horizontal direction. So let's quickly verify the values or the reduced value. So for the blue box, this one. So this pair is covering these two boxes. So the corresponding value of A is 0. So for these two boxes, A is 0. And the value of B, this is B, C, this is B and C. So the value of B is not changing, it is 1. The first value is in these two variables is B. The second variable, second number is C. Okay. Now what about C? C is changing from 1 to 0. Changing. Okay. So we can eliminate C. Since your value of A is 0, so you will get A dash. The value of B is 1, so you will get B. So the reduced form of these two boxes will be A dash B. Similarly here, the value of, for the brown box, the value of A, it is fixed. A is 1, which is fixed. And here the value of B is changing from, no, it is remaining same, B is 0. The value of C, it is changing from 0 to 1. Right? So we can ignore C. The value of A is 1, so I will get A. The value of B is 0, so that means I will get B dash. So this is my reduced form of the second pair. So finally, the reduced form of this given equation will be A dash B, this one, a dash b plus ab dash. Just add them together. That will reduce the. So you can practice a few questions. I will end the class today. There are a few more topics. We will study about them in the next class. Okay. So there are a few more topics. We will study about them in the next class. We can continue from here. Okay. So that should be all for today. And